Today I'll be presenting multi-arm bandit algorithms and how we use them to enable dynamic decision making in one of our products. So this is the first image that popped up when I searched multi-arm bandits on Wikipedia. Um, I was not very familiar with this concept, but I found it very interesting because it enables a wide variety of use cases and various applications. And this is the reason why I found it an interesting topic to present. But let's go back a little bit and talk about reinforcement learning. I'm sure most of you are familiar, but we'll do a quick recap. So what is reinforcement learning? It's basically a subset of AI algorithms like machine learning or deep learning. And the purpose of reinforcement learning is to learn what action to take in order to maximize the reward metric. So mapping situations to actions in simple words. There are some unique characteristics for for reinforcement learning. First of all, it's a closed loop, so the current actions can influence later inputs. So the actions are very important, and basically that's what the models have to learn. There are no direct instructions, so we don't have any training data set. And the consequences of actions can be longer term, meaning that the result is not to be observed immediately. And the most common issue that needs to be solved in reinforcement learning is balancing exploration and exploitation. So basically, that means trying to acquire new information while at the same time using the current knowledge to maximize the reward. So policies in reinforcement learning is basically the term used for models. A policy pi is mapping from states to actions, and this policy can be either deterministic or stochastic. And reinforcement learning algorithms can be on policy and off policy, meaning that on policy, the agent is learning the policy that it follows, so it gets updated in real time. And off policy is when there are two policies, basically, and the agent collects data using one of these policies, which is called the behavior policy, but learns about the optimal policy, which is called the target policy. Now, going back to multi-armed bandits and the image that I showed earlier, they are a very common reinforcement learning problem where a player has to repeatedly choose between a finite set of actions, meaning that each action provides a random reward from a specific distribution to that action. And the final objective is to maximize the total reward obtained after a number of rounds. And why is this helpful, other than slot machines and gambling? First of all, in healthcare, it can be used to find the best treatment while minimizing side effects. In finance, it can be used to maximize the yield of a portfolio by allocating funds to a finite set of instruments. And this is not financial advice, so don't take my word for it. And digital marketing, which is going to be our study case today, where you want to maximize a metric such as sales, clicks, or views in an A/B test. Now, what is A/B testing? I found this very suggestive image that I'll explain. So basically, when you make an A/B test, you want to split your visitors in a bunch of groups, at least two. And what you want is to show them different or slightly different variants of a web asset or app or any resource for that matter. And what you want is to monitor some metrics in order to find which of these options is the best. So our setup and what we had before we started prototyping multi-arm bandits was an A/B testing platform where traffic is normally allocated between these treatments or options with percentages defined by the clients of this platform. And what we basically wanted to achieve is adding multi-arm bandits and transitioning the manual allocation to something dynamic in order to facilitate this for our customers. For testing purposes, and the results I'll present a bit later, we had an ABC test with the conversion rates 6%, 2%, and 4.5%. In this case, the bandits can be considered Bernoulli because the actions are basically like coin tosses. So we wanted to maximize conversions, and in this case, conversions only have a yes or no outcome. So going back to this image, we determined that we need two things instead of the manual allocation. We need a smart AI-based decisioning engine that does this policy evaluation online. So each time a user accesses the resource that is under the A/B test, and basically this determines which option will be seen by the user during runtime. For that, we also need a reporting engine that is able to serve these metrics that we are using in real time, and it needs to be done fast because when you talk about the non-functional requirements for these services, the first one that any stakeholder will require is millisecond response time, because obviously a slow policy evaluation will result in a slow user experience, which will essentially make their web resource or platform less likely to be used. So therefore, online policy evaluations require a fast reporting engine. And for websites with a lot of traffic, there might be a necessity for big data processing pipeline in order to be able to deliver those metrics very fast. So talking about the algorithms that we used Thompson sampling, which is one of the most basic. We used another one called upper confidence bound, probably approximately correct. It's a funny name in my opinion. And lil UCB. And let's look a little bit further at these algorithms. The first one is Thompson sampling. As I said, it's the most basic one. It's called a beta Bernoulli bandit because it uses the beta distribution. As I said, we consider these events, the conversions or the people that don't convert, as coin tosses. So heads would be the number of heads would be given by the number of conversions, and the tails would be the number of people that don't convert. So each iteration, how it works is that it samples a number randomly from the beta distribution that happens at each arm, and then the arm with the maximum score is used. In simple words, this explores the possible option and gradually exploits the accumulated information. And to showcase the results, we have here a small plot. We ran around 4,000 tests in this setup, and we plotted the percentage of traffic allocation to the winner, so the 6% treatment. We can see that it goes pretty fast to the winning one, then it drops down a little bit, and then gradually gets to 100%. We further implemented this in one of our products in a different use case, and an issue that we discovered with Thompson sampling is that once the model accumulates a lot of information, it can prove that it's very hard to adapt to changes in the environment. So if one arm performed best for a long time, and now it no longer performs, and there's a different arm that is the best, it will be less favored to the one that has built up history. So in case you want to implement this, I'd recommend resetting the information one way or another. We also don't want to reset it completely, because all of the history would be lost. Next one was probably approximately correct. And this approach uses always valid confidence bounds. And it's great for choosing more than one winning option. But in our use case, we used it only for one, because we wanted to make a fair comparison. This is the formula for the confidence bounds. And basically, it uses conversion rate, obviously, because that's the metric we're looking to maximize. It uses the variance, which is fairly easy to calculate since all of our arms are Bernoulli. It uses the number of views, and it also has an uncertainty factor. So what this means is that for an uncertainty factor of 5%, let's say, the algorithm will give a winner or more winners with a 95% confidence. And it also uses a fine-tuning parameter that you can optimize if you run multiple iterations. This is the winner allocation that we got. It seemed pretty fair, since the exploration was around 30 to 40% for the first 1,500 iterations or so. And then after it found a winner, it maximized all of the traffic to it. Now, last but not least, we have little UCB. I found this algorithm very good. And the better brother of upper confidence bound. It uses the law of iterated logarithm, that's why the lil in the name. And it uses it to optimize the number of attempts to get to the winning variant. And we confirmed this hypothesis in our tests. Here's the formula that it uses for policy evaluation, where, as in the previous case, we use the conversion rate, number of views, and instead of an uncertainty factor, we have a certainty factor. So instead of 5%, you would use 95. There's also a couple of parameters that you can hypertune with grid search or other methods. And this is the winner allocation that we got. It was pretty good because it maximized the allocation to the winner fairly early compared to the other methods. And at the same time, it still kept exploring other possible options. Here's a result overview of all of the algorithms. We have Thompson sampling in the upper left corner. Next to it, upper confidence bound, which we didn't get very good results with it. I don't know if it doesn't fit to this use case, but for us it didn't really work. And we also have probably approximately correct and lil UCB below. I'll let these results for a couple of seconds so you can compare them head to head. Top right is upper confidence bound. Yeah, but in this case, it's not necessarily ideal to get to 100% because you want also to explore other options. So let's say today we have a 6% conversion rate on the winning arm. It maximizes to it. It keeps allocating all of the traffic to that. But tomorrow, the arm drops from 6% to 1%, and then let's say the one that had 2% goes to 10%, and you'll never you'll never get to that arm basically. Okay, so some conclusions about this little research that we made. It's that even though they're not very popular at the moment, they're a great way to optimize decision making across various sectors using AI and reinforcement learning. And there are a lot of initiatives and research literature on the subject. You can read more about advanced versions such as contextual bandits or collaborative bandits. However, from the research that I did, they're not very popular in production, or there's no like resources for products that use this. But after chatting with some people from different companies on this topic, I found out that they use them, but nobody talks about them. I also have some small project that I made to get to those results. You can access it on my GitHub, and feel free to create VRs if you find wrong stuff or you find better implementations of what I did. And here is a list of a couple of research papers that I found the best on the topics that I discussed, and these are the ones that helped me get a decent idea about this topic. Thank you very much, and if you want, we can connect on LinkedIn and GitHub. The QR code will give you the link to LinkedIn. Thank you very much.